Hi, welcome to the eCam channel. This is John. Today we are going to break down the analysis code CV Analyzer that was used in the previous tutorial. I hope this code will help you use this code with more confidence and have enough basic knowledge to create a program for your own project. I will briefly review the CV Analyzer program and the calculations, overview the outline of the code, break down the CV Analyzer program line by line with demos of functions, and end with a recording of my attempt at writing a new feature of calculating energy density and power density as an exercise. With the exercise, I hope to demonstrate a few troubleshooting methods as well. I will try to explain MATLAB basics along the way, but some background knowledge is probably needed. To briefly review what the CV Analyzer does, we can run this code to process the raw text files exported from biologic potential stat and produce 4 text files containing various analysis results. For the demonstration of the code, please watch tutorial 24. The exported results are summarized below. For detailed introduction on how to calculate these parameters, I list here some of our previous tutorials for your information. For converting current to specific capacitance, it is relatively simple. You can do that by dividing current by sweep rate and mass. For specific capacity, you can refer to tutorial 11. For specific capacitance, tutorial 3. For Coulombic efficiency, tutorial 23. For the number of electrons transferred per formula unit and the rate capability, tutorial 13. For B-value, tutorial 17. Of course, it will be tedious to keep going back to the previous tutorials to review the equations. Here is a cheat sheet for the calculations included in the CV Analyzer. We will input time, current, potential, and cycle number from the raw data and perform the calculations using the equations below. Many of the calculations are straightforward. The more tricky ones involve integration or regression. We will use a built-in trapezoidal integration function in MATLAB for the ones that require integrations. We will use a linear regression method to determine the b-value. The code can be roughly divided into 5 parts. The introduction teaches how to use the code. Then the user needs to input the mass of the active material, the number of cycles selected for analysis, and the molar mass of the active material. The part after this section should all be automated after the user clicks the play button. Data input is a section to extract the target information, which for us is time, potential current, and cycle number, and organize the information into a format that is easy to manipulate later. It involves the design of an automated procedure. I decided to use the number of header lines to eliminate the unnecessary text to single out pure data and use keywords like time, EWE to locate the columns containing the data we care about. I then extract the data from the number of cycles selected by the user and calculate the sweep rate of each text file using the basic definition of dV over dt. Lastly, I sort all data from lower sweep rate to greater sweep rate. I do this because sometimes the file name will mess up the ordering of the data. In the data processing step, I further sort and restructure the data so they can be easier to use for further analysis and be exported later as current versus potential and a specific capacitance versus potential at different sweep rates. Then we use the equations listed in the cheat sheet to perform all the calculations. In the last step, we export the results using the built-in MATLAB functions. This section turned out to be quite lengthy due to the formatting. In this section, we are going to break down the CV Analyzer program line by line. And here is a MATLAB user interface. I would like to just quickly go through the interface quickly. So on the left is the current folder we are in. So when you run the code, you're supposed to put this code together with the data exported from EasyLab software. In our case, if you have text files exported from other potential stat manufacturers, you will probably change the input part of this program to make it work. And in the center, we have the script of the code where it's the actual functions are written. And in the bottom is a command window where I can perform easy operations like 1 plus 1, or I can take out one of the code from the script to just test it. That's what I usually do. And whenever I run a code, if there are any error, it will also show up here. And on the right, it has a workspace. It shows all the parameters we saved. And on the top, we are usually in the editor tab. And when we want to run the code, we can just hit this run button. Next, we are going to dive into the code itself. So as we mentioned in the outline, that the first part is introduction, where it teaches how to use the code. And after that, there's a function called clear. What this does is, so I will enter clear in the command window. As you can see, before I hit enter, we have an answer of 2. That's from the 1 plus 1 we did before. If I hit clear, it will clear the workspace, so it will avoid the interference from previous runs of your code. And then in the user input places, in the user input section, we have 3 lines of code that asks the user to input the mass, molecular weight, and the second number that the user wants to analyze. In our case, we had 7 cycles, so I picked cycle number 4 for analysis. And the molecular weight I put here is the molecular weight for titanium carbide, and the mass is in the unit of gram. And this equal sign, which looks pretty straightforward, is called a assignment. So you are assigning this value to this name that's called mass. So if you click on this slashes on the left, you can and run the code. The code will stop at where your right circle is. So if I try this, you will see on the right that the mass and the molecular weight has the value has been assigned to these parameters. And because it stopped at the right circle, it didn't perform this line. And we can do that. Well, now you can see these 3 values have been assigned. And the next section is the data input. So we first need to load the file into the MATLAB. What I do here is there's a function that called dir. It reads the specified format from the directory. So here I specified star.mpt. So it's star is like any strings or characters that ends with the .mpt. So these are the default format from the ECLab. So if I run this line of code, you will see that it results in, so if you double click, it will open a new window that shows what the variables contains. And here you can see all these directory related informations. And this is a code that I found on the internet, and it helped me get all the file names that specified in the previous lines. So if I run this code, and by the way, the semicolon at the very end will, what it does is it stops the code from showing up in the command window. So if I do this code in the command window without the semicolon, it just spills out everything. And if I add a semicolon, it still assigns the values to all names, but it doesn't show up in the command window. So it helps clean up the command window a lot. And with this line of code, which is quite generic, all files is the last line of code, and it helps read. Sorry, not this one. It helps read out all the file names, as you can see shown on the left. So this is quite automated. And next, I would like to know how many files are there in this folder. So this NUMEL function stands for number of elements. So if we do this in the command window, we can see that we have 7 files, which is exactly the number of files we have. After that, we created 3 empty matrices, which will be used to contain cathodic capacity, anodic capacity, and sweep rate data in the future operations. These are required by the code just because of the way I write it. And this NaN function is called not a number. Yeah, so now you will see 7 not a number values be input here. What I like about not a number is, so in case this not a number shows up in origin, and when you plot it, those points will just be skipped. If you use 0 to construct a column, then 0 is actually a data point that will show up in origin plots. So I always use not a number as the placeholder. So we create empty matrices for the capacities and sweep rates. And next, we are going to encounter a loop that help us input the data. Loop is one of the main reasons we are using programming languages, because it will just repeat the same operation over and over again until you ask it to stop. So for here, I ask the function to start from 1, and with the spacing of 1, so it will be 1, 2, 3, 4, 5 until the number of elements. So here it's 7. So this loop, this function here, will run 7 times. And for MATLAB, for the loop to stop, we need to put an end here. So the end corresponds to the finish of the for loop here. As I introduced in the presentation, that I use the header line to determine how many lines of random text we have before we reach the actual data. So you can see the first 3 lines are just all the information that belongs to the text, and the number of header lines are actually provided by ECLab, like always. And here it auto specifies the number is 3. So I was taking advantage of that. What I did was I first turned the name of the first file. So I is the number that will cycle through that stand for each file. So the first file I will be 1, and when you read the second file, I will be 2. So in this case, when I run this file, turn this into a string that we can read, which we can then open the file, use the fopen function, and save it to a file ID. And the text scan function reads a text file into the MATLAB, and for this, I just ask it to read all the strings, which is the %s here. And the delimiter here, I didn't specify anything specifically. And then I will close this file. And because from our raw data, we know that here, the headlines always appears in the second line of the text file that ECLab exports. So here I will use a function. I'm not going to dive into the details of everything, but what this does, it extracts all the numbers from this line. Okay, I need to actually run the code. Okay, let me turn off the keyboard functions. So if you run this code, it will extract this value as 3. Okay, if you modify it, let me see. What we can find is now the number reads is 35. So basically what this function does is just reads any numerical values in the second line of the text. Okay, so I will change it back to 3, so it's correct. And the number of column is variable here is basically I want to find the number of columns in this text file. And this code does that. I'm not going to dive into the details. But what this code does is it basically reads the number of columns that you have in the code. For line 32, we'll actually come back later. But after we find the number of columns, what we need to do is we need to find the column that contains the data that we wanted. As we introduce, we want to extract the potential of a working electrode, the current, the cycle number, and time. So with ECLab, these are always the keyword that will be included in the title of the column. So I use them as keywords to look for the relevant data. And then here comes the time that we actually import the data. So we have obtained the number of headlines earlier. And here we use the FMT. That's the line we skipped before. So because here we actually wanted to import every single column, so we need a delimiter. And the delimiter we use here is %F. So each %F stands for a column of fractional data. And what I did here is we first calculate the number of columns, and this repmat function basically repeat this %F by 14 times. So if I copy paste below, so you will see we have 14 %Fs, and each of %F will extract a single column of data from the text file. This is just format requirement by MATLAB. Other software might be different. And we use the same text scan function from before, but this time we are just extracting the raw data in number format. And to select the data, so this is the new parameter I named data select. And because earlier we find the index, like basically the number of column that contains the potential data and all the other data. So I basically format it a little bit. So double is a formatting function. And raw data with this greater parentheses sign is used for cell type data, and basically we are extracting out these specific columns of data and save them into a new matrix called data select. So here we have potential index for current, for cycle number, and time. Notice that I divided this by 3600 because typically we use hours, like milliamp hour per gram, like this unit for capacity. That's why I divided this by 3600. And to demonstrate how what we have done so far, let me run this to the end. So first, let's see how the raw data look like. So after we read the raw data, you'll see we have 14 columns. That's what we specified before, and each one contains 15,310 rows of data. And based on these index numbers, for example, let's look at column number 9 for potential. So you can see the open circuit potential is about negative 0.3799, and it's being swept to lower potential at a constant sweep rate. And that's the raw data. And after we extract the data we want, we have the data select. That's this column here. So now you can see potential, current, cycle number, and time. The time doesn't start from 0 because we did some pre-cycling beforehand. Another, after we pick out the data select, I actually save it into a big matrix that actually contain all the data, because as I mentioned earlier, the text file names sometimes will mess up the ordering of the data. So I would like to sort them by the sweep rate, from lower sweep rate to larger sweep rate. And to do that, I need to save all the data into a huge cell that contains all the data. So basically what it does is it's a huge cell, and when you run this function over and over again, this will populate it until the 7th cell, because we have 7 data points. So let me demonstrate that. So here you can see the seven cells being populated after we run the loop for 7 times, and each of them contains the data collected at different sweep rates. And going back, we only typically pick one of the cycles for analysis. And here is how we do that. So basically I set up another for loop, and the method I used here is that I delete all the data unless the cycle number is number 4. That's the cycle number we select here. And let me rerun the code. In the data select here, we can see from the third column, that's the cycle number, we have cycle number 1, 2, 3, 4, 5, 6, and 7. So you'll see all this data. And the only thing we want is the data that contains has the third column of number 4 here. So there are smarter ways to do this, but what I did here is I set up another loop that's inside the first loop. This basically goes through 1 to the maximum number of cycles here. So you see this is 7, so there's maximum amount of cycles contained at this sweep rate. So it will go through each of these values, and one is not equal to, so this approximate sign followed by an equal sign is actually means not equal to. So when it's not equal to the cycle number, I will delete that line of data. So let me run this code. So after this, all the data has been eliminated. Only the column number 4 is remained. Okay, so that's how we select the data from cycle number 4 for further analysis. And the last thing we do before we jump to the sorting is calculating the sweep rate. Because the sweep rate is not always provided by the ECLab software, I decided to calculate myself using delta V over delta T, which is the definition of the code. And to improve the accuracy, I pick out the cathodic limit potential and the anodic limit potential values. So the function here is called min and max. It selects the minimum and max, the maximal point of data. So if I try this code, it will just provide the value. So the lowest potential we cycle to our CV2 is negative 1.15 volt. And the highest potential we cycle our cell to was negative 0.05 volt. So the bracket before the min and max functions gives the index of when this minimum or maximum value happens. So if we do this, we will see now the first parameter is the minimum value of potential, and the second one contains the number of data. So if we go to data select and this parentheses column comma 1 parentheses back, so this one here means selecting all the rows from column 1. So if we look at column 1 and see if this value is correct, so we want to go to row 772. So 772 give us 1.15. That's indeed the lowest value we have in this cycle. So similarly, max is basically the same function. So we determine the lowest and highest potential. Then because all the data are corresponded, so we know the last data point is time in hours, and we can directly calculate the sweep rate. So the sweep rate original is delta V over delta T. So how do we tell which ones are potential? The potentials are the first column of the data select, and time is the fourth column of the data select. and we divided this by 3600 so that it's back to the unit of second, and we multiply by 1000 because typically sweep rates are in the unit of millivolts per second, and the default voltage is in the unit of volt, as you can see here. Usually when we calculate this number, it's not an integer. So let me try this. It's sweep rate of 100 millivolts per second. However, it's not an integer. So this line here, I try to determine the order of magnitude of this sweep rate. So what I used a log10 function. It will tell me the magnitude in general, but it will also not be an integer. So log 10 of this value, like 100 point something, the value will be very close to 2. So floor is round this number downwards. So if it's 0.1, it will be rounded to 2. So that the n will always be an integer in my case. So because we sometimes will have sweep rates less than 1, so like 0.1 millivolts per second for batteries, so we separate it into a few different cases, and so I will round it differently. So here we use the function round. Basically, it tells you to round it to a certain significant numbers. Let's say for 0.1, then for 0.1, the n will equal to -1. So here we will actually have 1 plus 2. So we will have 3 significant numbers. So we have 0.1, and for 100 millivolts per second, there are chances you will calculate like 101, but you still want to only save for the 100 millivolts per second because you know 101 is only an error. So in this case, this function, what it does is it will remove the last single digit. So let's say we have 101, and when 101 n is equal to 2, okay, so you will see the value it output is 100. So basically it removed the last single digit from 100 millivolts per second. So basically this function rounds the sweep rate to 2 significant numbers. This is the end of what's written inside this for loop, and for each cycle of this for loop, basically extract the header line, read the columns, get the data, select the number of cycles for analysis, calculate the sweep rate, and these steps will be repeated for each text file. And since sweep rate is all over the place, I would like to order them. I will not go through these order functions in details. Usually for any programming class, it's one of the must taught part. I forgot which one I used here, but it works. And after you run this part, let's look at sweep rates again. And now you see the sweep rates are now ordered from smaller values to a greater value. And one thing to note here is at the same time I reordered sweep rates, I also reordered the data select all. So the data select all, if you remember, contains all the, where is it? Contains the 7 column, which follows the same order as the sweep rate. So I sort it at the same time as my sweep rates, so the data in the cells are also sorted at the same time. So if we go back to our outline, we have now introduced the data input part of our function. And next, we are going to enter the data processing section. Next, we are going to talk about the data processing section. So here you will see another for loop. You will notice every time I use a for loop, I use the variable I, so it will be replaced over and over again and be renewed in every new for loop. The first thing I did, which at first might look very confusing, is I select the number of cycles again, just to review what we did, because we did all of our operations on data select, but after we calculate sweep rate and stuff, when we sort the data, we actually sorted the data select all. So the sorted data has not been treated at all. So what I did here is I assigned the I number of cells from data select back to this name of data select all, back to this name variable data select. And after that, I did this selecting the number of cycle for analysis code again. So that's exactly the same as before. After we get the proper data select with the known sweep rate and in an order that's what we want, I will sort the data or restructure the data for future export and further manipulation. Here I finally did something nice, that I named this very abstract data select into a new variable. So I assigned the first column to EWE, that's working electrode potential, and the second column divided by the mass, so that's specific current, to I, and group them into a matrix of 2 columns, so that's EI. Let me run this. So EI basically provides 2 columns, the first column being potential and the second column being the specific current. And what I want to use this in the future is I want to export them for easy plotting. And we also calculate specific capacitance at each potential value by dividing specific current by the sweep rate. This we get another variable called EC, so this column contains the specific capacitance at each potential value from that sweep rate. This is different from the average capacitance value from the anodic or cathodic cycle, and this is just an instant value. Something different here is because I want the data to be plotted easily, here's a bunch of operations I did to concatenate matrices. It looks quite complicated. I will show what it does first. And previously we only have 2 columns of data, but now we have 14 columns of data. And you will see the effect at the end of the last few rows of the data. So in MATLAB, to put different matrices together, it has to be have the same length, and the number of rows. And because each different sweep rate may have different number of data, it depends on your electrochemistry setup. It may contain different number of data points, and sometimes some cycles may have more data points than the other, and you have to accommodate for that. The very complicated function we write here basically will fill this not a number value to wherever the columns that didn't have enough rows of data in there. So it's, for example, especially for rows 13 and 14, it filled up many of these NaN rows, so that these columns can be put together, and when we export them, this data will not be plotted in plotting softwares like Origin. And next, I did a calculation of cathodic and anodic capacities and capacitance. So for the capacity and capacitance calculation, let's do a quick review that we first divided into cathodic and anodic cycles, and the cathodic cycle is when current is less than 0, and when anodic cycle is current larger than 0 in our case. And for the capacity, specific capacity, we are integrating the specific current over time. And for specific capacitance, we divided the specific capacity values by the potential window. So here, I first picked out the current and time value for the integration. That's the negative current and time and positive current and time. And the functions I use is basically, I know data select, the fourth column of data select is time, and the second column is current. So I basically made a matrix with two columns, the first one being time, the second one being current. I select the time only when the current value is less than 0. So that's basically the definition of this value. We can plot this to see if it works. So if you plot the first column by the second column, you can see that this is in the fourth cycle, and this is your open circuit potential, and you go from here, you go to your lowest potential, then you go back to the anodic cycle that's above here, and then you come back to the open circuit potential. And when we perform the integration, we are basically integrating the current from here to here, and then it's 0, so there's nothing, then here to here. So that's the integration we do in this case. And you can also see the anodic cycle by plotting it. So here you see the only anodic cycle. Because of the selection of open circuit potential, the anodic cycle will look much simpler than the cathodic cycle, which got divided into two parts. We will perform the trapezoidal integration, which is quite simple, where you use this trapz function and input time. So this is the x-axis, and current, that's the y-axis. I divide it by the mass, so it's specific current. That's how you get the specific capacity. I save it to the ith element because if you remember, very earlier we created a column called cas cap and anode cap. So for the specific capacity of cathodic cycle and a specific capacity of anodic cycle. And we use them here as we need to store these values. And the ABS here shows it's a absolute value because cathodic current will be giving us negative current, and when we report it, we only report the absolute value of that. So that's how we calculate the specific capacities for cathodic and anodic cycles. Then we need to calculate the capacitance. So first thing we need to do is we need to know the potential window. And again, here we have the rounding issues. So the basic function is we want to know the potential window, and it's basically the largest potential minus the smallest potential we cycle to. A bunch of other things I added here is to round it to an appropriate significant number, because I know if I just do this minus, the potential stat is not perfect. So if you do like the max potential, I know my max potential was set to negative 0.05, but it was wrong to negative 0.0512. So using this function, it helps me get to the appropriate significant numbers not fooled by the potential stat artifacts. By definition, it's relatively simple to convert the specific capacity, which here I use the unit of milliamp hour per gram. And here to convert it to farad per gram, I multiply by 3.6. This is basically multiplied by 3600 to convert from hour to second, then divided by 1000 to convert milliamp to amp. So amp second divided by voltage is farad. That's by definition. So with this operation, we get capacitance in the unit of farad per gram. This is the end of this for loop. So this will be, again, number of elements is equal to 7. So it will be repeated for 7 times. And we will have the Castle cap. So we will have the specific capacity from lower sweep rate to higher sweep rate. And we also have the capacitance. You'll see it's one is ordered in row and the other is ordered in column, because I guess I was not careful enough. But the reported value of 350 to 200 is in ballpark similar to what's reported in the literature for TSCC2 in sulfuric acid. Next, we are going to calculate the Coulombic efficiency, the number of electrons stored in the formula, and the read capability. The equations are listed here. And when we go back, it's nothing fancy. As you can see from the equation, it's just numerical operations, division, multiplication. We multiply the Coulombic efficiency by 100, so it's in the unit of percent. This is Faraday's law of electrolysis. This is Faraday's constant, and this is the unit conversion. We use the molecular weight that the user inputted in the beginning, and the rate capability is according to definition as well. So there's nothing too fancy here. Next, we are going to perform the p-value analysis. So for p-value analysis, we are using the basic definition of p-values from the anodic cycle. We will choose the highest current from the anodic cycle of each sweep rate of cycle number 4. We will determine the maximum current. We have used this max function before. What's important to us here is the location of the maximum current. We also calculate the value of maximum, the potential at the maximum current using the max location variable, because we want this to be exported so we can plot it to show to audience and readers. And the max sort function is purely for export purposes, and the log for b is for actual calculation. So this function, in this function, we convert the sweep rate to log scale. So this is log e, and we also convert max I also into the log e scale. There's a function to do linear regression in MATLAB called polyfit, and we'll use the order of 1. So this is basically linear regression, and we can calculate the slope and the intercept, and slope will give us the actual b value. So we already got the b value from the slope. Next, for statistical purpose, we need to calculate the how good the fit is. For plotting purpose, we created this fit variable, which contains 2 data points, which is the first with the lowest sweep rate and the fitted value and the highest sweep rate and the corresponding fitted log I value, and this will help us plot the function in origin later. To calculate the r squared, that's the r squared here, we use the function of r squared that you can find on Google, and I just converted into a MATLAB code. It's also basic operations, just make sure the unit is correct. And here something special about MATLAB is I used a dot to the power of 2. This needs to be used when we are operating matrices. Lastly, we will go through the results output section. For the result output section, we are basically following what the MATLAB wants. For it to be exported, it needs a file name. So basically, we will open a file. So this will be a text file. Then we can write into it, and in the end, we close the file. And then the file, after we hit run, the file will be saved. The important thing here is I want to have headers followed by values because this will be origin friendly. The fprintf is basically print these values into the file ID. That's the file we just opened. These functions here are space holders. So %string is strings you can put in here, and 10 means I reserve 10 spaces for the string, and \t is a delimiter. What I find, this space doesn't really matter. They are here for historic reasons, and the only thing you need to be careful is the last data point is /r and /n. This is to say this is the end of the column, and \n switch to the next line. After that, we can input the values to be filled into these strings. So we have sweep rate, voltage window, specific capacity, analytic specific capacity. So the first thing we are exporting are the sweep rate dependent analyses. So read capability in the analytic cycles, so on and so forth. So you see these are all the names be filled into the strings. And then the next line, I want to print their unit. So similar idea, I have the space holder and the actual units. Lastly, I want to input all the columns of data. So data is input in the format of fraction, because they are fractional numbers. Here, the 0.1 is actually important because that tells you the number of digits after the point. So 0.1 will give you accuracy to 0.1, and 0.5 will give you accuracy to 0.00001. To import this, I have to create a new matrix for this purpose. So basically, I group the sweep rates, the potential window, the capacities, capacitance. You see a prime here because if you remember from earlier, the capacity are in vertical direction and the capacitance are in horizontal direction. So I use the prime to just convert it. So you see the values are like this, but if I do a prime, then they will be listed in the vertical form. Then you have Coulombic efficiency and all the other values be contained in this matrix, and I will export it. It's demanded by the format of MATLAB that it has actually. So if we look at this, compiled analysis. So these are everything are listed in columns. It looks quite clean, but it's demanded by MATLAB. If you want to export it as is, you actually need to invert it first. So here's another prime here. And one thing I forgot to mention that there are 2 primes with nothing in there. That just means that column doesn't have a unit, like number of electrons stored per formula unit doesn't have a unit. So it's a space holder there. Yeah, so Now this text file has already been exported, so all the text file from the potential stat is MPT, and text file we export is TXT. So this is what we just calculated. And next I'm going to talk about the exporting for the B values. So again, it's the same idea. We create a name for the file. I use something called strrep, so it's like replacing part of the string. The purpose of that is to I forgot to go over that in the previous section, but basically replace part of the word name with what you want. Like here I put in the .txt for the format and the log b for because this is for b value analysis. Previously the analysis is for sweep rate dependent analyses, and I know that this title of the text file doesn't make too much sense because part of it is just getting cropped, but it's informative enough to tell me which file it is. The purpose to include these strings is because sometimes if you do too many of these analyses, things start to get messy, and with part of the original file name of the in the beginning, it helps you identify which data file it actually belongs to. And again, we open the file. These values are what we want to export it. We basically did some data restructuring. If you remember, P1, that's the fit. The P1 is the slope, which is the actual B value. I put in a bunch of not a number here for formatting purposes. And the fit here contains the fitted linear regression line. This resized R square is the R square value resized for formatting. So when I compare everything together, they become this matrix. So we have the log sweep rate and the log current converted to log scale. This is only for plotting purposes. The fitted line, the B value, and R square all contained in one matrix. And then the header, the unit, and the actual values. So let's run this again. So there will be another text exported, and you can see, so these are the log sweep rate, log current, the fitted lines, B value, and R square. And next, we are going to export the current and potential. This part looks complicated and contains a lot of lines of code, but the main purpose of this is because we want it to be robust. Sometimes people want to analyze like 5 files with 5 different sweep rates. Sometimes people want to analyze like 14 files with 14 different sweep rates. So this code, we try to make it flexible enough to accommodate all sweep rates. And here the name has _e and _i in there because it contains potential and current data for plotting purposes. I also included the recessed peak is the peaks we used for b-value analysis. So if you want to plot it for b-value analysis, you can use this file. This resize is basically contain a bunch of not a number in order to be compiled into one matrix with the current and potential and current data. What I did here is basically I go through a bunch of for loop options to accommodate for the number of data. So the number of element is what we need for our regular potential and current, but we also added the peak current we use for b-value analysis. So it's we added an additional column, and so we just loop through this 8 times, and we will every time we will just write into the first row of the text file until we reach the 8th time of this for loop, and we print potential and current basically titles into the file, switch to the next line, and then we print the unit, potential, and specific current milliamp per gram. We input the sweep rate. So this is just a I guess smart way to input the sweep rate. So number to string is convert a number to a string. So we can compile so that because when we put matrices together, the data type have to be the same. And using this function, we convert the sweep rate to strings, and it can be put together with millivolts per second. It's also just for plotting purposes. And we know the last 2 columns are peak potentials and peak current. So these will be like the comments in the origin. And lastly, we have the data. So if you remember, we need the value holder. Then we need the actual data itself. Then after we print all over our numerical values, we close the file. The capacitance is very similar. This time we don't need the resized peaks. So this something I forgot to mention is that this percentage sign are comments that will not be processed when you run the code. So I copy paste this code from earlier section and then modify it, but I was too lazy to just delete this code, so I just comment them out so they won't be skipped when you run the functions. And we go through the same thing, except that we don't have the peak current and the peak potential. So we remove 1 plus 1 from the for loops. All the other is the same. I probably should use specific capacitance here. Specific capacitance. Here's the unit. Here's the comments that contains the sweep rate. We create a value holder to contain the potential and the capacitance values, and then we close the file. That's about it. So if we run everything down, and it should be, we asked it to stop here, so I need to remove these red dots. Let it continue. Okay, it finished the code. So now 2 new files are created that it's formatted as what we wanted. So we have the potential current with the unit of milliamp per gram, the sweep rate, and the actual values. And if you want to put in the reference electrode information, then you will come here. Let's say if you want to voltage versus silver chloride, you can do that. And if you run this code, you will see that the code will be updated. And if you look at here, you will see the unit has been converted to volts versus silver chloride. That's about it about this code. I'm sure I missed a lot of stuff, so if you have questions, please leave them in the comment section below. It really takes exercise to learn a language. Since a comment in the previous video asked for power density features, I decided to include this as an exercise. I will provide a recording of how I write this feature next, but you are encouraged to write this one on your own if you are interested in learning this method. Here I provide the equations for energy density and power density calculation from CV. To amend the code, I imagine we need to take 3 steps. First, find out the voltage and time difference. Then perform the calculations. Lastly, export the data. So here is a recording of me trying to write a feature to include power density and energy density. It's additional features, so I don't need to change too much. And as you can see from the equations, it's mainly we need to calculate the delta V and delta T because anodic and the cathodic capacity has already been calculated. So with these two values, we will be good to go. So I know, so first of all, let me save it to a new file called exercise. I know that I will be needing 4 more matrices for energy density and power density. So I will be creating cathodic energy. How do I want to name it? And I don't want too long names. Density. I'll just be copy pasting these part. So I have anodic counterpart. Has the power density and anodic power density. Okay, and a good habit is comment the line as you write it, because 3 months later you will forget everything. And here contains the cathodic energy density, and copy pasting, change it to anodic, and change it to power, anodic power density. Here we go. So I know this is where we calculate the capacity. So I will try to divide them. So this is capacitance, specific capacitance. So this will be specific energy density because it's normalized per mass. And later we'll have specific power density, and it will equal to something, but let's comment it out first. Ctrl R can convert that line to a comment. And according to the equation, we want to know the voltage difference, and it's actually something tricky because if you remember, the data didn't look that good. So if you remember that when I plot the first column versus the second column, it got separated apart. And let me try plotting something different, because from the potential perspective, may not look that bad. So I'll be plotting this too, but instead of current, I change it to potential. So that's first column. Let's see how it goes. So here we go. So I think this is the point we want for the final voltage, and this is the beginning voltage, because like somewhere here is the open circuit voltage. In current as a function of time, it got broken up, but in the potential profile, it looked okay, and we are looking for the intersection with I equal to 0. So we need to find a way to locate this V. How do we do that? Let me go back to the previous plot, because I know the potential will reach its the VF will be reached at this point, and the V0 will be reached at this point, and all I need to do is to just find these two data points, and all these data points are continuous, so it will be data point 1, 2, 3, 4, 5, and let's say this is 100, and it will jump like from data point 100 to 200. The time data will jump significantly, whereas anywhere else on the curve it will be a linear change. So all we need to do is to find this point, and we'll be good. So what I would like to do is I would like to look at the data, and oh, wait a minute, I think we have a simpler solution. So if we look at the positive side, these two values are the potential values, right? And what we need to do is we can find I can say something like EI positive, where I just copy paste this function and change time to potential and time to potential. All right. So let's run this code in the command window. Okay. EI pos. Here we go. Yeah, negative 1.06 to negative 0.06. That's pretty much what we read from here. Wait. Oh, this is time. So let me try again. What we plotted earlier. So 1.06 to positive 1.06, negative 1.06. Yep, so this is the value, pretty close to what we want. And we can say V0 is equal to EI pos. This is matrix, have column and rows, and separated by a comma. And this the first one will just be to select the last row. It will be and first column. So 1 and VF is equal to the first data point of the first column. Let's try this. So V0. Oh, wait a minute, I messed up. So it should be the other way around. Yep, so the first number is the number of rows. Wait, no semicolon. Okay, here we go, we have the proper value. And VF, we have, yep, these are the value we want. And delta potential is V0 minus VF. And we get about 1 volt potential window. It helped me auto-corrected one value, a typo, which looks about right. Yep. And to calculate the specific energy, we want this to save to the ice element, and according to the equation is cathodic capacity divided by delta V. Sorry, multiplied by delta V. And the similar idea applies to the analytic side. Here we go. So that's your specific energy density. And then you want to calculate specific power density. And according to the equation, it needs to be divided by the delta T. Oof. So that's the time spent on the energy storage. So it'll be easier for the analytic cycle, trickier for the cathodic cycle, just because it got segmented into 2 parts. So, and the delta T analytic. Let's stick to the naming convention. Put analytic first. Delta T is equal to probably the first data point, last data point minus the first data point. Okay, let's see what it does. Okay, we have some unit issues. So I see. So specific capacity has a unit of, let's see what unit we want. So right now it's milliamp hour per gram times volt. If we wanted to convert it to volts per gram, is equal to amp second, this is equal to coulomb times voltage. sorry, not volt, joule per gram. And that should be the definition of joule. So basically that we need the same type of conversion, so we need to multiply by 3600 seconds divided by 1 hour, then divided by 1000 to convert it from milliamp to amp. So then we have the appropriate unit, so we need to multiply this value by 3.6. So we have unit of joule per gram. If you want watt hour per gram, you'll need to do a different conversion that you convert it back to hour. And okay, let's go back to the power density calculation. So we have the time difference, and because we have to convert the units from hour to seconds, we want to do that here as well. So we want to multiply by 3600 to convert it to second. Okay, so it's 10 seconds something. And we want to calculate the time in the cathodic cycle as well. This will be trickier. What can we do? Let's look at the data again. So IT neg. We want to see the plot again. So we need to find where this data jump ahead. And find the gap in cathodic cycle. For that, I will write a for loop. We already have I, we have J. I'll write something. No, like K. We'll run from 1 to the number of elements in this column, and I just want to select one column so it doesn't double count. And inside this, I would like to see I'll do -1 because I want to do a subtraction and don't want to run out of space. I want to do diff t is equal to k plus 1 minus k. And if diff t is greater than set a standard. So it will be pretty constant. So I will say diff t0 will be the second data point minus the first data point. So if this is 100 times, well, I would say 10 times greater than the standard, it means it's a gap. Then we will record K, gap index is equal to K. This K, it may not be correct. We will need to test it out. And let's take a look. See if the code runs. No, the code doesn't run. We have an issue in the specific capacity, a specific energy density function. Unable to perform assignment because the left and right side have different number of elements. I see, because I forgot to put in I here. Okay, let's try again. Okay, it finishes. Let's see what's the gap index are. Gap index says 922. Okay, let's take a look. IT negative, and we go to data 922. Okay, so we jumped from here to here. So that's a pretty big jump. Yeah, so basically 922 give us the gap value. Okay, yeah, we can see the difference in time more clearly than the current, which should be obvious. And well, so this function served its purpose, and we successfully identified where the gap is. And with that, I would like to calculate cathodic time difference. So it will be IT negative from gap index 1 minus IT negative 1, because that's before the gap. Okay, plus the one after the gap. So it will be IT negative and 1, so that's the last data point, minus IT negative gap index plus 1, because negative plus 922 plus 1 is here. And yep, and the summation of these two multiplied by 3600 should give you the value in second. Let's see what this value gives. Boom. 1.24 times. Okay, let me calculate this again. Okay, so cathodic is much longer than anodic. Does that make sense? Let me check. So 3.6189. The last data point here is 3.845. I'm just manually checking this whether it makes sense. Sorry, I forgot to put a minus sign between. Okay. These two are basically similar. Yeah, that's basically the same thing. And we can do some checking here. So we have So we have 9.55 minus 9.54, 771. Sorry, should have more digits. 6 plus 9.5538 minus 9.55292. Wait, what? Oh, the data has changed. I need to plot this again. Okay, so it's a different plot now. Here we go. All right. So we come here, replace the values. 3.61866, 3. Plus 3.97449 minus 3.88475. All right, yeah, that's actually the same. That's actually the same as what we calculated from before. Okay. And let's go back to our analysis. Yeah, so this equation seems to be correct. And according to this equation, the power density is basically, how do you rename? I think it's PW. Is equal to this divided by cos del T, and we'll have anodic power density equal to anodic energy density I divided by anodic delta T. Okay, and yeah, so these are the values that we calculated. Cool. And to export, Well, this will be a sweep rate dependent thing. I'll export it. Well, we can export it in the front. So power density, analytic power density, let's copy paste this. Energy density. Okay, I forgot to input the unit. So the unit here will be watt per gram. Okay, I basically need 4 data points, so I just copy 1, 2, 3, 4 of the segments, and I will say something like specific power density, and copy paste again. Change the second one to energy density. Change the unit. So we want after volts will be two of these. We'll have volt per gram. What's the unit for energy? Joule per gram. Then we want more data points for the data. Then we hit run. Let's see if we got something new. Analysis. Okay. Something doesn't look proper. Let me drag this into Excel. So say power density. Okay, something wrong with the okay, something inappropriate happened that I probably didn't do some of the copy pasting properly. Oh, I see, because of the unit I forgot to copy paste 4 copies. Do it again. Oh, and because I opened the file. Don't save, run it again. Boom. Drag it into Excel. Okay, now this data looks more proper. At least the values. Wait a minute. Okay, cathodic, anodic. There's something wrong here. Anodic specific energy density, anodic specific capacity. I did something wrong with the let's see how it goes. Okay, this looks more appropriate. Yeah. Yeah, there's a huge difference in, well, not so big of a difference in capacity, but the energy density is really different. Well, when Coulombic efficiency gets better, it gets better. The main difference is the hydrogen evolution reaction at lower sweep rates. The Coulombic efficiency was pretty bad, like 66%. Okay. Yeah, so here is the exercise where you have sort out the data, calculate the value, and export it in a text file. I hope this video provides you with the necessary information to understand and modify the CV Analyzer program. I hope it is useful for some of you. If you have any questions, please leave them in the comment section below. The videos in our eCam channel are only for educational purposes and knowledge sharing. Please subscribe, share, and like our videos to support our channel. Thank you for watching the video today. See you next time.